Hi everyone, we are back here talking about insulation, and right now we're going to discuss R values. Why are we discussing R values? Obviously it's the most characteristic material property used to describe insulation. So here on this graph we're just showing some typical R values. You can see the close-held spray foam, typical R values for common insulation. Close-held spray foam has the highest R value this is a per inch value. And then on the lower side, we've got wood fiber board. So what is R value? R value, simply put, is describing a material's ability to resist heat flow. Because again, this is all about how are we controlling flows across our boundary in relationship to the thermal control layer. We want to make sure that our thermal control layer effectively resists the flow of heat across it. So that's what the R value is describing. Your material's property, ability to resist that heat flow. In terms of R values, this is basic, but the higher the better. We could break down what the units mean, but in terms of R value, it's a little hard to get into. When we look at the U factor, it's a little bit easier to understand. The U factor is the inverse of the R value. It describes the property of a material to conduct heat. And you can see from the units, I like describing this better because it does make more intuitive sense. You can see from the units that we're talking about an amount of heat, unit of heat per temperature difference per unit time per area. I don't know if that makes sense without really digging into it, but to me that does make more intuitive sense. So in the case, because it is, the U factor is an inverse, the lower the better. R value, the higher the better. U factor, lower the better. R value is what you're going to hear talked about when we're dealing with insulation. U factor is what you will hear referenced in terms of windows. Also with, you might hear the term UA calculations, which are an average U factor calculation for an entire building envelope. That's used often to prove compliance with an energy code using a performance path. This slide here is just showing that relationship between R value and U factor. You can get a U factor by dividing 1 by the R value, and vice versa. You can get the R value by dividing 1 by the U factor. There are a couple things that are important to note about U factors versus R values, and we will discuss that later on. So coming up next, we're going to talk about the direction of flows. It's sort of the nature of things that we will be addressing. We are here now talking about driving forces, direction of flows. Why are we doing this? Because we want for you all to be thinking intuitively about your buildings, your homes, as systems, and as systems that are subjected to elements of nature, and that system needs to function effectively in controlling flows. So I keep on saying that. I realize that, but that is at the heart of the matter. So So we'll just go through a few straightforward examples, and the point here again is to create this intuitive sense about how to think about buildings maybe a little differently than you are right now. So we could look at gravity. And obviously the direction of flow is from more to less. And I say obviously, but maybe it isn't actually obvious, because what happens is that objects are moving from a higher energy state to a lower energy state. So would love to talk about that in context of basic physics, Newtonian physics, but we won't. But just remember, more to less, right? When we're talking about a concentration, temperature gradient, we are talking, again, you will hear people describe the second law of thermodynamics as heat moving from hot to cold. And I think it's pretty snobby of people to disagree with that description, but maybe to not get the physics snobs' backs up, we could describe it like this. When we're talking about temperature differences, remember the point here is to understand intuitively which direction our heat flow is going to move. It's always going to move from higher concentration to lesser concentration. So more energy is associated with heat, higher concentration of energy to an area of lower concentration. This is very practically important when we talk about differences, gradients, temperature differences, temperature gradients across our building envelope, which is our boundary again. The thing to understand about this is that the higher that difference, the bigger that difference between indoor and outdoor, whether it's in the summer or in the winter, the higher, faster, more the heat flow will be across our boundary. Generally, winter presents the higher temperature gradient, which is why we see in very cold climates higher insulation requirements. We could look at this in terms of air pressure gradients, which move, which dictate our weather patterns globally. We could look at this in terms of concentration gradients, which could be vapor concentration. So this is what dictates vapor drive across boundaries. Osmotic pressure gradients, which again is having to do with water concentrations across boundaries. So again, the message here is you have flows moving in the direction of a higher concentration to a lower concentration. And with that, we will leave off with our overview of putting insulation and control layers into the context of building science, and we'll talk about some specifics about types of insulation.